As you settle into the comfort of your bed tonight, let your thoughts drift toward a journey across landscapes where the earth itself breathes fire. Perhaps you've seen images of molten rock cascading down mountainsides. Or maybe you've stood at the edge of an ancient crater, feeling the subtle warmth rising from below. Tonight, we'll explore these magnificent features of our world, volcanoes, not as threats or spectacles, but as windows into the living, breathing nature of our planet. The word volcano comes to us from ancient times, from Volcano, a small island north of Sicily, where the Romans believed Vulcan, their god of fire, forged weapons in underground furnaces. When smoke and fire rose from the island's peak, they imagined the god was working at his forge, hammering out thunderbolts for Jupiter or crafting armor for the heroes of legend. This early association between volcanoes and divine creation speaks to something we still understand today, that these fiery mountains are places of transformation where the very substance of Earth is reshaped before our eyes. As you rest, imagine the Earth beneath you, not as a solid, unchanging foundation, but as a series of layers, each with its own character and movement. At the very center lies the inner core, a solid sphere of iron and nickel surrounded by the outer core, a churning sea of liquid metal that creates our planet's magnetic field. Above this sits the mantle, thousands of miles thick, made of solid rock that nevertheless flows over vast spans of time, moving with the slow patience of geological processes. And finally, the thin crust upon which we live, a mere skin compared to the planet's full depth, like the delicate shell of an egg. Volcanoes begin their story deep within the mantle, where temperatures reach thousands of degrees. Here, solid rock behaves like an extremely slow-moving fluid. Currents of heat rise and fall through the mantle in a process called convection, the same principle that moves the air in your room, though on a vastly different time scale. As this heat rises, it sometimes carries with it molten rock or magma, which collects in chambers beneath the Earth's surface. When conditions allow, this magma finds pathways upward through weaknesses in the crust, eventually reaching the surface as lava, the visible breath of the Earth's interior. There is a certain peace in understanding that the same principles that govern a pot of simmering soup on your stove also control the movement of continents and the birth of mountains. These connections remind us that the extraordinary and the everyday are woven from the same fabric, following the same patient laws of physics. In this way, volcanoes are not alien or separate from our experience, but extensions of familiar processes, magnified to a scale that stretches our imagination. Not all volcanoes share the same temperament. Some are explosive and unpredictable, while others flow with relative gentleness and consistency. This difference comes primarily from the composition of their magma, specifically how much silica it contains and how much gas is dissolved within it. Magma rich in silica becomes thick and sticky, trapping gases that build pressure until they escape violently. Think of it as the difference between honey and water. One flows freely, while the other traps air bubbles and moves with reluctance. Shield volcanoes, like those that form the Hawaiian Islands, typically erupt fluid basaltic lava that flows easily across the landscape. Their eruptions are relatively gentle, creating wide, gently sloping mountains built layer by layer from thousands of lava flows. Mauna Loa, rising from the floor of the Pacific Ocean to create part of the island of Hawaii, is the largest mountain on Earth when measured from its true base, taller even than Mount Everest if we consider its full height from seafloor to summit. In contrast, stratovolcanoes or composite volcanoes such as Mount Fuji in Japan or Mount Rainier in the United States are built from alternating layers of lava flows, ash, and rocks ejected during eruptions. Their magma is typically richer in silica, making for more explosive eruptions that can send ash miles into the atmosphere. These volcanoes form the iconic cone shapes that most people picture when they think of volcanic mountains, steep-sided, symmetrical peaks that dominate the surrounding landscape. Then there are the caldera volcanoes, vast depressions formed when a volcano's magma chamber empties during an eruption, causing the overlying land to collapse inward. Yellowstone in the western United States is perhaps the most famous example, a massive volcanic system so large that many visitors don't even realize they are standing inside a volcano as they watch geysers erupt or marvel at colorful hot springs. Calderas remind us that sometimes the most profound forces work in ways we can barely recognize, shaping our world through processes that unfold over tens of thousands of years. In the slow, peaceful hours of night, it's fitting to consider the time scales of volcanoes. While some erupt frequently, Hawaii's Kilauea has been erupting almost continuously since 1983. Others may sleep for centuries or millennia before awakening. Vesuvius, the volcano that buried Pompeii in 79 CE, had been dormant so long before that eruption that the Romans living nearby didn't even recognize it as a volcano. Vineyards and farms covered its slopes, and people had forgotten the danger that lumbered beneath their feet. This pattern of sleep and awakening gives volcanoes a rhythm that mirrors our own cycles of rest and activity, though stretched across vastly different spans of time. As you lie in bed, your breathing slow and regular, imagine the earth also breathing, not with the quick cadence of human lungs, but with exhalations that might come centuries apart. There is a certain comfort in this perspective, in seeing ourselves as part of these greater cycles rather than separate from them. Volcanoes also create as they destroy. When lava cools and solidifies, it forms new land. The Hawaiian Islands themselves are monuments to this creative power, a chain of volcanic mountains that have risen from the seafloor, one after another, as the Pacific tectonic plate moves over a hot spot in the mantle below. Each island represents millions of years of patient accumulation, lava flow upon lava flow, building new territory from the planet's fiery interior. In Iceland, where the mid-Atlantic ridge rises above sea level, one can actually watch this process of creation in real time. The island straddles two tectonic plates, the North American and Eurasian, that are slowly moving apart. Volcanic eruptions fill the gap between them, creating new land in one of the few places on Earth where we can actually see the planet growing before our eyes. During the eruption of Surtsey in 1963, sailors watched in awe as a new island rose from the sea over the course of several months, a birth witnessed within a human lifetime. The soils around the volcanoes are often remarkably fertile, enriched by minerals brought up from deep within the earth. Some of the world's most productive agricultural regions sit in the shadow of volcanoes, where generations of farmers have benefited from the same forces that occasionally threaten their existence. In Italy, the slopes of Vesuvius support thriving vineyards. In Indonesia, terraced rice fields climb the flanks of volcanoes. This fertility represents another facet of volcanic systems, their role in Earth's chemical cycles, bringing elements from the planet's interior to its surface where they can nourish life. As night deepens around you, let your thoughts drift to the sea floor, where most of Earth's volcanic activity actually occurs, hidden beneath miles of water. Along the mid-ocean ridges, vast underwater mountain chains that wind like seams around the globe, new seafloor is constantly being created as magma rises to fill the gaps between separating tectonic plates. These submarine eruptions happen far from human eyes, in darkness broken only by the faint glow of molten rock meeting frigid seawater. In these depths, a remarkable ecosystem has evolved around hydrothermal vents, fissures in the ocean floor where mineral-rich water, heated by volcanic activity, streams into the surrounding sea. Here, in the absence of sunlight, bacteria harness the chemical energy of these mineral-laden waters to produce food, forming the base of a food web that supports communities of strange and wonderful creatures. Giant tube worms with bright red plumes, blind shrimp, and ghostly white crabs thrive in this seemingly hostile environment, a reminder that life finds pathways to existence even in the most extreme conditions. The discovery of these hydrothermal communities in the 1970s revolutionized our understanding of where and how life might evolve. Some scientists now speculate that life on Earth might have originated in similar environments, nurtured by the chemical energy and mineral wealth provided by underwater volcanic activity. In this view, volcanoes are not merely features of our planet, but perhaps fundamental to the very emergence of life, architects not just of land, but of the living world itself. Volcanic islands scattered across the world's oceans offer another perspective on the creative power of these geological features. When underwater volcanoes rise high enough to break the ocean's surface, they create new land masses that begin as barren rock, devoid of life. Yet over time, these islands become cradles of evolution as plants and animals arrive, carried by wind, waves, or wings, and adapt to their isolated new homes. The Galapagos Islands, where Charles Darwin found inspiration for his theory of evolution by natural selection, are volcanic in origin. Each island in the archipelago represents a different stage in the life cycle of a volcanic system, from the youngest islands with active volcanoes to the oldest, where erosion has worn down the volcanic peaks to low hills. As Darwin observed, the isolation of these islands allowed unique species to evolve, adapted to the specific conditions of their volcanic homes. The famous Galapagos tortoises, finches, and marine iguanas are all products of volcanic creation, not directly, but through the opportunity these new lands provided for life to explore new evolutionary paths. Hawaii offers another example of this process, with each island in the chain representing a different stage in volcanic evolution. The oldest islands to the northwest have been weathered by millions of years of wind and rain, their volcanic origins softened by time. The newest island, the Big Island of Hawaii, still grows through active eruptions. Its fresh lava flows a stark reminder of the ongoing processes that built the entire chain. Between these extremes lie islands in various stages of erosion and biological colonization, a linear record of how volcanic lands age and change. As you rest, consider the vocabulary we use for volcanoes, a language that acknowledges their living qualities. We speak of volcanoes being active, dormant, or extinct, terms that suggest a life cycle not unlike our own. We describe eruptions as events with beginnings and endings, phases and changes. Even the word eruption itself carries connotations of something held back and then released, a pattern familiar from our own experiences of emotion and expression. Perhaps this tendency to see volcanoes in human terms reflects a deeper truth. That we and they are expressions of the same planet, different manifestations of Earth's ongoing creativity. The same elements that comprise volcanic rock also flow through our own bodies, rearranged into different patterns but fundamentally the same materials. The carbon, hydrogen, oxygen, and nitrogen that make up our tissues have cycled through Earth's systems for billions of years, some released from the planet's interior through volcanic activity. Ancient peoples intuited this connection between volcanoes and life. In Hawaii, the volcano goddess Pele was not merely a destroyer but a creator, shaping the land through her fiery temperament. Her relationship with the Hawaiian Islands was complex, sometimes antagonistic, sometimes nurturing, but always integral to their existence. Similar figures appear in mythologies around the world, from the Aztec fire god Xiuhtecutli to the Roman Vulcan, each representing human attempts to understand and relate to these powerful forces. The Greeks told stories of Hephaestus, whom the Romans later called Vulcan, the smith of the gods who worked in a forge beneath Mount Etna in Sicily. When the volcano erupted, they said it was the sparks from his hammer or the heat from his furnace breaking through to the surface. This personification of volcanic activity helped make sense of a phenomenon that must have seemed both terrifying and wondrous to people without our scientific understanding. In Indonesia, where hundreds of volcanoes dot the archipelago, traditional beliefs often view these mountains as sacred places where spirits dwell. Ceremonies and offerings are still made to maintain harmony with these powerful entities. When Mount Merapi, one of Java's most active volcanoes, shows signs of unrest, a spiritual guardian appointed by the local sultanate performs rituals to appease the mountain spirit. These practices reflect a worldview that sees volcanoes not as mindless geological processes but as conscious presences with which humans must maintain relationships. Such perspectives remind us that there are many ways to understand and relate to natural phenomena. Our scientific knowledge gives us one kind of insight into volcanoes, explaining their mechanics, predicting their behaviors, analyzing their products, but traditional knowledge systems offer another kind of wisdom, one that emphasizes our relationship with these features and their place in the broader web of existence. Both approaches have value, and together they give us a fuller picture of what volcanoes mean in human experience. As night continues its gentle passage, let's turn our attention to some of the ways volcanoes have shaped human history. The eruption of Terra, now known as Santorini, in the Mediterranean around 1650 BCE, was one of the largest volcanic events in recorded history. The explosion collapsed the center of the island into the sea, leaving behind the crescent-shaped rim that forms today's Santorini. Some scholars believe this eruption contributed to the decline of the Minoan civilization on nearby Crete, either through direct damage from tsunamis or through climate effects that disrupted agriculture. Similarly, the massive eruption of Indonesia's Mount Tambora in 1815 produced the Year Without a Summer in 1816, when volcanic ash circling the globe reduced sunlight and lowered the temperatures worldwide. Crops failed across North America, Europe, and Asia. In New England, snow fell in June. In China, rice fields froze in summer, leading to widespread famine. This climatic disruption inspired cultural changes as well. Mary Shelley wrote Frankenstein during the gloomy summer she spent confined indoors by persistent rain and cold in Switzerland, a direct result of Tambora's eruption thousands of miles away. These events highlight the interconnectedness of Earth's systems, how a volcanic eruption in one place can affect weather and human affairs around the world. They remind us that we live on a planet where distant events are never truly separate from our experience, where causes and effects ripple outward in complex patterns that we are only beginning to fully understand. Yet, for all their potential to disrupt, volcanoes have also created conditions that supported human development. Some of the world's earliest civilizations arose in volcanic regions, drawn by the fertile soils and useful materials these areas provide. Obsidian, a volcanic glass formed when certain lavas cool rapidly, was among the first traded materials in human history. Its ability to be knapped into extremely sharp tools and weapons made it highly valued, and archaeologists have tracked ancient trade networks by identifying the specific volcanoes from which obsidian artifacts originated. In regions like the highlands of Guatemala and Mexico, civilizations including the Maya and Aztec used obsidian for everything from religious ceremonies to daily tools. The abundance of this resource, along with the agricultural productivity of volcanic soils, helped support the development of complex societies in these areas. Similar patterns can be seen in other volcanic regions around the world, from the Mediterranean to the Pacific Rim, where human communities have long maintained relationships with these dynamic landscapes. The minerals and metals brought to Earth's surface by volcanic activity have also played crucial roles in human technological development. Many important ore deposits form in association with volcanic systems as mineral-rich fluids circulate through rocks, concentrating valuable elements in veins and replacement bodies. Copper, gold, silver, and numerous other metals vital to human civilization are often found in abundance in volcanic terrains. In this way, volcanoes have not only shaped the physical landscape but have provided resources that enable the growth of human societies and technologies. Let your thoughts drift now to the different forms volcanoes can take beyond the familiar cone shape. Some volcanoes barely look like mountains at all. Fissure eruptions occur when magma reaches the surface through long cracks in the Earth's crust rather than through a central vent. These eruptions produce curtains of fire as lava fountains along the length of the fissure, sometimes extending for miles. Iceland's lucky eruption of 1783 was of this type, pouring forth enough lava to cover nearly 500 square miles of land. Then there are flood basalts, vast outpourings of fluid lava that can cover thousands of square miles. The Columbia River basalts in the northwestern United States, the Deccan Traps in India, and the Siberian Traps in Russia are examples of these enormous features. The Siberian Traps eruption, which occurred about 250 million years ago, coincided with the largest mass extinction in Earth's history, the Permian-Triassic extinction event. The massive release of gases from these eruptions likely triggered catastrophic climate change, demonstrating the profound impact volcanic activity can have on Earth's living systems. Mud volcanoes represent yet another variation, where pressurized gases and liquids force mixtures of mud and water to the surface. Though not true volcanoes in the sense of involving magma, they create similar features, cones, craters, and flows, but made of mud rather than molten rock. Azerbaijan is home to nearly half of the world's mud volcanoes, strange bubbling features that occasionally burst into flame when methane released from below ignites upon contact with the air. As you continue to rest, consider the subtle ways volcanoes affect our daily lives, even for those who have never seen one in person. The ash ejected during major eruptions contains minerals that eventually weather into components of soil, nourishing plants across vast regions. Volcanic rocks like pumice are used as abrasives in everything from cosmetics to industrial polishing. The carbon dioxide released by volcanoes, though far less than human emissions, plays a role in Earth's natural carbon cycle, a background process that has helped regulate our planet's temperature for billions of years. Even the water we drink may have volcanic connections. Some scientists believe that a significant portion of Earth's water was delivered not by comets or asteroids, as commonly thought, but through outgassing from the planet's interior via volcanic eruptions in the early history of our world. If true, this would mean that the water in your glass, the clouds overhead, and the oceans that cover most of our planet's surface all have their ultimate origins in Earth's fiery depths, brought to the surface breath by volcanic breath over billions of years. This perspective transforms our understanding of volcanoes from occasional disruptive events to integral components of the systems that make Earth habitable. Without volcanic activity recycling material between the planet's interior and surface, many of the cycles that support life would eventually grind to a halt. Volcanoes are not separate from the living world, but are vital participants in its ongoing maintenance and evolution. In recent decades, scientists have developed increasingly sophisticated methods for monitoring volcanic activity and predicting eruptions. Seismometers detect the subtle tremors that often precede eruptions as magma moves beneath the surface. Gas monitors track changes in the composition and volume of emissions from vents and fumaroles, which can signal shifts in the underlying magmatic system. Ground deformation measurements, using both physical benchmarks and satellite radar, can detect the swelling of a volcano as magma accumulates beneath it. These technologies allow volcanologists to issue warnings when eruptions seem imminent, potentially saving thousands of lives. Yet prediction remains an inexact science. Each volcano has its own personality, its own patterns of behavior that may not perfectly match those of others. Some give clear warning signs before erupting, while others can surprise even experienced observers. This individuality reminds us that, for all our scientific advancement, volcanoes retain an element of mystery, a reminder of the complexity and unpredictability inherent in natural systems. As the quiet hours pass, consider the volcanoes that sleep beneath the ice. Antarctica, a continent we associate with extreme cold, hosts several active volcanoes, including Mount Erebus, which features one of the world's few persistent lava lakes, a pool of molten rock that remains liquid at the surface for years or decades. The heat from this and other Antarctic volcanoes affects the movement of ice sheets above them, creating meltwater that lubricates their flow toward the sea. In Iceland, subglacial eruptions create distinctive flat-topped mountains called tuyas. When a volcano erupts beneath an ice sheet, the ice constrains the lava's spread, forcing it to pile up within a cavity melted in the overlying glacier. The interaction between molten rock and ice produces distinctive rock formations and can lead to sudden, catastrophic floods called Jökullaups when meltwater accumulated beneath the ice suddenly breaks free. These ice-covered volcanoes illustrate the remarkable diversity of volcanic environments on Earth. From the ocean depths to tropical islands, from desert plains to polar ice caps, volcanic activity manifests in countless ways, each adapted to its particular circumstances yet governed by the same fundamental processes. This ubiquity speaks to the essential role volcanoes play in our planet's systems. They are not anomalies but expressions of Earth's basic nature. The relationship between the volcanoes and climate is complex and bidirectional. Large eruptions can cool the planet temporarily by injecting aerosols into the upper atmosphere, where they reflect sunlight back to space. The 1815 eruption of Tambora, mentioned earlier, caused a global cooling of about 1 degree Celsius on average, enough to disrupt agriculture worldwide. Yet over longer time periods, volcanic emissions of carbon dioxide have helped maintain Earth's greenhouse effect, preventing the planet from freezing and allowing liquid water to persist on the surface. Some researchers suggest that periods of intense volcanic activity in Earth's past contributed to ancient climate changes, including both warming and cooling episodes that shaped the evolution of life. The massive flood basalt eruptions that coincided with major extinction events likely released enormous quantities of both cooling sulfur aerosols and warming greenhouse gases, creating complex climate effects that stressed ecosystems beyond their capacity to adapt. Conversely, climate can affect volcanic activity as well. As ice sheets grow and shrink during glacial cycles, the changing weight of ice on Earth's crust can increase or decrease pressure on underlying magma chambers. Some studies suggest that the rapid melting of ice at the end of the last ice age, around 12,000 years ago, triggered an increase in volcanic eruptions in regions that had been ice-covered. As today's glaciers and ice sheets melt due to human-caused climate change, scientists are monitoring whether similar effects might occur in the volcanic regions currently under ice. As your thoughts continue to drift through these geological landscapes, imagine the varied textures of volcanic rocks. Smooth, glassy obsidian forms when silica-rich lava cools so quickly that crystals don't have time to grow. Rough, vesicular pumice, so light it can float on water, forms when lava full of gas bubbles solidifies before the gases can escape, leaving behind a rock that is mostly air. Basalt, dark and dense, breaks into distinctive columnar shapes as it cools and contracts, creating formations like the Giant's Causeway in Ireland or Devil's Tower in Wyoming. These different rock types tell stories about the conditions under which they formed, the composition of the original magma, how quickly or slowly it cooled, whether it was rich in dissolved gases or relatively dry. A trained geologist can read these stones like pages in Earth's autobiography, deciphering events that occurred millions of years ago from the texture, mineral content, and structure of the rocks they left behind. For those who know how to look, even landscapes far from active volcanoes may reveal volcanic origins. The rolling hills of Tuscany, the dramatic cliffs of the Scottish Hebrides, the flat plains of eastern Washington state, all were shaped by volcanic processes in the distant past. These ancient volcanic landscapes have been transformed by erosion, burial, uplift, and other geological processes, yet they still bear the signatures of their fiery beginnings for those who know how to recognize them. This perspective expands our understanding of volcanoes from discrete events or individual mountains to an ongoing process fundamental to Earth's nature. Volcanic activity has been part of our planet since its earliest days, shaping continents, contributing to the formation of the atmosphere and oceans, and creating conditions conducive to the emergence and evolution of life. We live on a volcanic planet, whether or not we can see an active volcano from our window. As night deepens toward dawn, let your thoughts turn to the sounds of volcanoes. An eruption is not just a visual spectacle but an acoustic one as well. The deep rumble of moving magma, the hiss of escaping gas, the crack and pop of cooling lava, the thunderous explosions of pyroclastic eruptions. Volcanoes speak in a language of sound as well as heat and light. Some eruptions produce infrasound, vibrations at frequencies below human hearing that can nevertheless be felt as a pressure in the chest or detected with specialized instruments. Hawaiian traditions recognize the importance of listening to a volcano. Elders speak of paying attention to the sounds coming from Kilauea, different tones and rhythms that indicate different types of activity or messages from Pele. This auditory awareness represents a kind of knowledge gained through generations of close observation, a way of understanding volcanic behavior that complements modern scientific monitoring. In the quiet of your room, imagine these sounds, not as threatening roars, but as the voice of a planet in conversation with itself, exchanging matter and energy between interior and surface in a dialogue that has continued for billions of years. Like breathing, like heartbeats, like the cycling of seasons, volcanic rhythms are part of Earth's ongoing life, neither good nor bad, but simply expressions of its nature. Among the most fascinating volcanic features are lava tubes, natural tunnels formed when the surface of a lava flow cools and solidifies, while the still molten interior continues to flow, eventually draining away to leave a hollow conduit. These tubes can extend for miles, creating underground passages large enough to walk through. On the Moon and Mars, planetary scientists have identified similar features that could someday provide natural shelter for human explorers, protecting them from radiation and extreme temperature fluctuations on the surface. The existence of these extraterrestrial lava tubes reminds us that volcanism is not unique to Earth but occurs throughout the solar system. Venus is covered with volcanic features, including enormous shield volcanoes and vast plains of solidified lava. Mars hosts Olympus Mons, the largest known volcano in the solar system, rising nearly 15 miles above the surrounding terrain and spanning a width comparable to the entire state of Arizona. Even tiny Mercury shows evidence of ancient volcanic activity, despite its small size. Beyond the inner planets, different forms of volcanism occur. On Jupiter's moon Io, the most volcanically active body in the solar system, eruptions of sulfur compounds create colorful plumes visible to spacecraft. On Saturn's moon Enceladus and Jupiter's moon Europa, evidence suggests eruptions of liquid water rather than molten rock. Cryovolcanism driven by tidal heating of subsurface oceans. These diverse manifestations of volcanism across the solar system highlight both the universality of the underlying principles and the creative variations that emerge under different conditions. Human responses to volcanoes have always been complex, blending fear, awe, respect, and practical adaptation. In Japan, hot springs heated by volcanic activity have been used for bathing and healing for centuries. In Iceland, geothermal energy provides clean, renewable power and heat for homes and businesses. In Hawaii, volcanic soils support agriculture, while the dramatic landscapes draw tourists from around the world. These relationships show how human communities have found ways to benefit from volcanic processes while respecting their power. Modern society continues to develop new applications for volcanic materials and energy. Volcanic rock wool is used for insulation, lightweight concrete, and hydroponic growing media. Volcanic ash improves cement strength and durability. Geothermal power plants tap into underground heat sources, often of volcanic origin, to generate electricity without burning fossil fuels. Research continues into techniques for capturing carbon dioxide from the atmosphere and injecting it into basaltic rocks, where it can react to form stable minerals, potentially helping address climate change. These innovative uses of volcanic resources represent a continuation of humanity's long relationship with these dynamic geological systems. Throughout history, people have found ways to live with and benefit from volcanoes while respecting their potential dangers, a balance that requires both scientific understanding and cultural wisdom. The study of volcanoes extends beyond Earth science to include their influences on biology, climate, human history, and culture. Volcanologists work alongside archaeologists to understand how eruptions affected ancient civilizations, with climatologists to assess volcanic impacts on global weather patterns, with ecologists to document how life recolonizes landscapes after eruptions, and with engineers to design structures that can withstand volcanic hazards. This interdisciplinary approach reflects the interconnected nature of Earth's systems, how a process that begins deep in the mantle can ultimately affect everything from atmospheric chemistry to human migration patterns to the evolution of species on newly formed islands. Volcanoes remind us that boundaries between scientific disciplines, like those between Earth's spheres, are human constructions rather than natural divisions. As dawn approaches, consider one final aspect of volcanoes: their role as windows into Earth's interior. The materials they bring to the surface, gases, lavas, crystal-rich rocks, and fragments torn from the walls of their conduits, provide our most direct samples of the otherwise inaccessible depths. By analyzing these materials, scientists can infer conditions deep below the surface, mapping the composition, temperature, and pressure regimes of regions we can never visit in person. Some volcanic rocks contain inclusions called cyanoliths, literally foreign rocks, that were picked up by rising magma on its journey to the surface. These fragments can originate in the lower crust or upper mantle, regions otherwise known only through indirect geophysical methods. By studying xenoliths, geologists gain glimpses of these hidden realms, piecing together a more complete picture of Earth's internal structure and composition. Similarly, volcanic gases provide information about chemical processes occurring far below the surface. The ratios of different gas species, isotopic compositions, and changes in emission rates over time all offer clues about the source and behavior of magma. These invisible emissions, though less dramatic than flowing lava or billowing ash clouds, are among the most valuable indicators for scientists monitoring volcanic activity and assessing potential hazards. In this way, volcanoes serve not just as expressions of Earth's inner nature, but as messengers from a realm beyond human reach. They bring to light materials and processes that would otherwise remain hidden, allowing us to study our planet more completely than would be possible through surface observations alone. They are natural laboratories where the extreme conditions of Earth's interior temporarily connect with the accessible world of its surface, creating opportunities for discovery and understanding. As you drift towards sleep, imagine these connections between deep and shallow, between ancient and present, between geological and human timescales. Volcanoes embody such connections, standing at the thresholds between different aspects of Earth's being. They remind us that our planet is not compartmentalized, but integrated, its systems linked through exchanges of matter and energy that have continued since its formation. In this integration lies a kind of harmony, not despite but because of the dynamic, sometimes destructive nature of volcanic processes. The same forces that occasionally disrupt human activities also create conditions that support life over longer timescales. The ash that darkens skies eventually enriches soils. The lava that buries landscapes creates new land. The gases that can temporarily alter climate have helped maintain Earth's habitability over billions of years. This broader perspective doesn't diminish the very real hazards volcanoes pose to communities living nearby, but it places those hazards within a context of ongoing planetary processes essential to Earth's nature. It invites us to approach volcanoes not just as threats to be monitored and mitigated, but as integral features of the living system we inhabit, neither benevolent nor malevolent, but simply being what they are, expressions of a planet that remains dynamic and creative after more than 4 billion years. Within this continuous planetary breeding, certain volcanoes stand as monuments to nature's most profound displays of power. Krakatoa, an island volcano in Indonesia, erupted in 1883 with such force that its sound was heard nearly 3,000 miles away in Australia, and its atmospheric pressure wave circled the Earth several times. The explosion destroyed most of the island, leaving behind a collapsed caldera beneath the sea. Tsunamis triggered by the eruption killed more than 36,000 people on nearby shores. The ash and aerosols injected into the stratosphere created vivid red sunsets around the world for years afterward, inspiring paintings by artists who may not have known the source of the unusual colors that filled their evening skies. Imagine those sunsets, skies painted in shades of crimson and purple that had rarely been seen before, all because of tiny particles suspended high above, catching the last rays of the setting sun. These particles, too small to see individually, collectively transformed the light reaching Earth's surface, creating a global aesthetic effect that linked people across continents in a shared experience of beauty. Even as the eruption brought destruction to those nearby, it created a moment of unwitting connection among people far removed from the event itself, a reminder of how Earth's systems link us all in ways we may not immediately recognize. The 21st century has brought new tools for understanding and appreciating volcanic processes. Satellite imagery allows us to observe eruptions in remote areas that once would have gone unnoticed or unstudied. Thermal sensors can detect heat anomalies that might signal rising magma before any visible changes occur at the surface. Drones equipped with cameras and sampling devices can enter volcanic plumes or fly over active craters, gathering data that would be too dangerous for human researchers to collect directly. These technologies extend our senses, allowing us to perceive aspects of volcanic activity that would otherwise remain hidden. Yet, for all this technological sophistication, there remains something profoundly humbling about standing near an active volcano. The heat rising from the ground, the subtle smell of sulfur in the air, the occasional rumble of movement far below, these sensory experiences connect us directly with Earth's power in ways that digital data cannot. Visitors to active volcanic areas often describe a sense of perspective, a recognition of their own smallness against the backdrop of geological forces that have shaped the planet for billions of years. In Hawaii, where the volcano goddess Pele remains a living presence for many native Hawaiians, this connection takes on spiritual dimensions. Offerings of flowers, food, or gin are still left at the edges of Kilauea's crater, acknowledgments of Pele's power and sovereignty over the volcanic landscape. These practices reflect a relationship with volcanic forces based not only on fear or risk management, but on respect and reciprocity, an understanding that humans are participants in, not controllers of, the systems that shape the islands. Similar relationships exist in volcanic regions around the world. In Bali, the sacred Mount Agung hosts important temples at various elevations on its slopes, with the mother temple Purai Besaki situated high on the mountainside. When Agung shows signs of activity, religious leaders interpret these changes through both traditional knowledge and in consultation with scientific monitoring agencies. This integration of spiritual and scientific approaches represents a more holistic way of relating to volcanic landscapes, one that honors both cultural heritage and contemporary understanding. As you rest, consider the concept of time as expressed through a volcanic activity. Different processes unfold at vastly different rates, from the explosive violence of an eruption that transforms a landscape in minutes to the patient buildup of a volcanic island over millions of years. A single volcano may exhibit different time scales in different aspects of its behavior. The magma feeding it may move slowly for decades, while gas emissions might change hour by hour. The mountain itself might grow over centuries but be partially destroyed in a single day. This multiplicity of time scales offers a different way of perceiving time itself, not as a simple linear progression, but as a complex interweaving of cycles and processes, each with its own rhythm and pace. Fast and slow, sudden and gradual coexist within the same system, creating patterns too complex to be captured by any single measurement, but rich with information when viewed from multiple perspectives. Human history has been punctuated by volcanic events that altered not just landscapes but the course of civilizations. When Huayna Putina in Peru erupted in 1600, the climate effects were felt globally, with 1601 becoming the coldest year in 6 centuries for the Northern Hemisphere. Russia experienced such severe crop failures that the resulting famine, combined with political instability, led to the collapse of the Tsardom of Russia and the rise of a new dynasty. A volcanic eruption in South America thus contributed to reshaping the political landscape of Eastern Europe, an example of how Earth's systems can create unexpected connections across great distances. The destruction of Pompeii and Herculaneum by Mount Vesuvius in 79 CE offers a different kind of historical insight. The volcanic ash that buried these Roman towns also preserved them in remarkable detail, creating an archaeological treasure trove that has provided invaluable information about daily life in the ancient world. Bread, still in ovens, bodies frozen in their final positions, wall paintings with colors still vibrant, these snapshots of ordinary moments transformed into extraordinary records precisely because of the catastrophe that ended them. From destruction came preservation, a paradox that speaks to the complex legacy of volcanic events in human experience. More recently, the eruption of Iceland's Eyjafjallajökull in 2010 caused relatively little local damage but grounded flights across Europe for weeks due to the dangerous clouds posed to aircraft engines. This disruption revealed the vulnerability of modern transportation systems to volcanic activity and led to improvements in tracking and modeling ash dispersal. It also provided an unexpected glimpse of clearer skies over Europe as thousands of flights were cancelled, briefly reducing aviation's contribution to air pollution and carbon emissions, a reminder of the complex interconnections between natural events, human systems, and environmental conditions. The relationship between volcanoes and climate deserves deeper exploration as you continue to rest. Beyond the short-term cooling effects of major eruptions, volcanic activity has played crucial roles in Earth's long-term climate stability. Over geological timescales, volcanoes release carbon dioxide that helps maintain the greenhouse effect, preventing the planet from freezing entirely. The weathering of volcanic rocks also serves as a carbon sink, as certain minerals react with atmospheric carbon dioxide and eventually carry it to the oceans, where it can be incorporated into marine sediments. This balance between volcanic carbon sources and sinks forms part of Earth's thermostat, a self-regulating system that has helped maintain conditions suitable for liquid water and therefore life for billions of years despite changes in solar output and other factors. When this system is examined alongside the water cycle, nutrient cycles, and other planetary processes, volcanoes emerge as key components in a complex network that sustains Earth's habitability through various feedback mechanisms operating across different timescales. The concept of Earth as a system of interconnected processes, sometimes called Earth system science, offers a framework for understanding volcanoes not as isolated features, but as nodes in a network, both influencing and influenced by the other components of the planetary system. This perspective emphasizes relationships rather than boundaries, flows rather than fixed states, and integration rather than isolation, a more holistic approach to Earth science that parallels indigenous understandings of nature as fundamentally interconnected. As night deepens around you, imagine the chambers beneath volcanoes, where magma gathers before rising toward the surface. These are not simple reservoirs but complex zones where multiple processes occur simultaneously. Crystals form and settle as the magma cools slightly. Different minerals solidify at different temperatures, changing the composition of the remaining liquid. Gases dissolved in the magma begin to form bubbles as pressure decreases. New magma may enter from below, mixing with or displacing what was already there. Recent research using techniques like seismic tomography, which uses seismic waves to create images of Earth's interior similar to how medical CT scans image the human body, has revealed that these magma chambers are often more complex than previously thought. Rather than being single, large cavities filled with liquid magma, they may be networks of smaller interconnected spaces, some filled with crystals and only partially molten. This crystal mush behaves differently from fully liquid magma, affecting how the volcano erupts and what materials it brings to the surface. Understanding these subsurface complexities helps explain why volcanoes can behave in seemingly unpredictable ways, why some eruptions begin suddenly while others provide clear warning signs, why some volcanoes produce consistent eruption styles, while others vary dramatically from one event to the next. Each volcanic system has its own internal architecture, its own history of activity that has shaped its current structure, and its own particular combination of factors influencing its behavior. This individuality extends to the landscapes volcanoes create. Over time, erosion, weathering, and the growth of vegetation transform fresh volcanic deposits into distinctive terrains. In wet climates, volcanic soils develop quickly, supporting lush forests or productive farmland. In drier regions, volcanic landscapes may remain stark and seemingly barren for centuries, their dark rocks slowly colonized by lichens and other pioneer species that gradually prepare the way for more complex ecosystems. The island of Surtsey, born from a submarine eruption of Iceland's coast in the 1960s, has provided scientists with a unique opportunity to observe this process of biological colonization from its very beginning. Within a few years, the first plants, mainly beach grass and other coastal species, had established themselves from seeds carried by ocean currents or birds. Insects arrived, followed by nesting seabirds. Soil began to form as organic matter accumulated and weathering broke down the volcanic rocks. Today, several decades later, the island hosts a growing community of plants and animals, a laboratory for studying ecological succession on newly created land. Similar processes have played out countless times throughout Earth's history, as volcanic activity created new surfaces for life to colonize. The Hawaiian Islands represent different stages in this progression, from the newest areas on the Big Island, where fresh lava flows remain largely unvegetated, to the oldest islands in the northwest, where millions of years of weathering and ecological succession have created deeply eroded landscapes covered with rich soils and diverse ecosystems. This pattern of creation, transformation, and eventual erosion forms part of the life cycle of volcanic systems. Individual eruptions come and go, but the broader processes continue, rebuilding what erosion tears down, bringing new material to the surface as older deposits are weathered away or subducted back into the mantle. In this cycling of material between Earth's surface and interior, volcanoes serve as conduits, pathways for exchange that maintain the planet's dynamism over geological time. The products of this exchange include not just rocks and gases, but also elements essential to life: phosphorus, potassium, calcium, magnesium, and various trace elements reach Earth's surface through volcanic activity, eventually becoming available to living organisms through weathering and other processes. In this way, volcanoes contribute to the chemical fertility of the planet, providing nutrients that support ecosystems both on land and in the oceans. Some of these elements become concentrated in deposits that humans have learned to extract and use. Sulfur, used in countless industrial processes, has been harvested from volcanic regions for thousands of years. Pumice, the frothy rock formed from gas-rich lava, has been used as an abrasive since ancient times. Obsidian, as mentioned earlier, provided some of humanity's earliest tools. Even diamonds sometimes reach the surface through a type of volcanic eruption called a kimberlite pipe, which brings material from deep in the mantle where high pressure can create these precious crystals. These resources represent another facet of humanity's relationship with volcanic systems, our ability to find value and utility in their product even as we remain vulnerable to their hazards. This duality reflects the broader human experience of living on a dynamic planet, where the same forces that create conditions for life and provide resources also present challenges and risks that must be navigated. Let your mind drift now to the boundaries between tectonic plates, where much of Earth's volcanic activity is concentrated. At divergent boundaries, where plates move apart from each other, magma rises to fill the gap, creating new crust. The Mid-Atlantic Ridge, mentioned earlier in the context of Iceland, represents this type of boundary, a global seam where the seafloor spreads at a rate of a few centimeters per year, pushing the Americas farther from Europe and Africa over geological time. At convergent boundaries, where plates move toward each other, one plate may slide beneath the other in a process called subduction. As the descending plate moves deeper into the mantle, increasing pressure and temperature cause water and other volatile components to be released from the rocks. These fluids lower the melting point of the surrounding mantle material, generating magma that rises to form volcanoes. The Ring of Fire, the belt of volcanic and seismic activity surrounding much of the Pacific Ocean, follows these subduction zones, where oceanic plates dive beneath continental plates or other oceanic plates. Transform boundaries, where plates slide horizontally past each other, typically produce earthquakes rather than volcanoes. However, they can create conditions that influence volcanic activity in adjacent regions by changing stress patterns in the crust or creating pathways for magma movement. The complex three-dimensional geometry of plate boundaries, combined with variations in crust thickness, heat flow, and other factors, helps explain the global distribution of volcanic activity, why some regions experience frequent eruptions while others have remained volcanically quiet for millions of years. Within this global framework, individual volcanic systems develop their own characteristics based on local conditions and history. Some form isolated mountains, while others create ranges or fields of multiple vents. Some build steep cones, while others produce vast plateaus. Some erupt frequently but mildly, while others sleep for centuries before awakening with catastrophic force. This diversity defies a simple classification but offers endless opportunities for exploration and understanding. As night continues its gentle passage, consider the submarine volcanoes that dot the ocean floor, most of them hidden from human view until relatively recently. Advances in oceanographic technology, deep-sea submersibles, remotely operated vehicles, autonomous underwater drones have allowed scientists to explore these features directly, revealing volcanic landscapes as varied and complex as those on land. Submarine eruptions differ from their terrestrial counterparts due to the enormous pressure of the overlying water column. This pressure prevents the explosive expansion of volcanic gases that creates dramatic ash plumes on land. Instead, submarine eruptions tend to produce distinctive features like pillow lavas, rounded lobes formed as molten rock is rapidly chilled by contact with seawater. These pillows stack atop one another, creating structures that resemble piles of cushions or tubes. When broken open, they often reveal a glassy outer crust surrounding a more crystalline interior, a record of different cooling rates as the lava solidified. At some mid-ocean ridges, a different type of volcanic activity occurs. Rather than erupting lava, these systems expel superheated water through the vents in the seafloor. These hydrothermal vents form when seawater seeps into the crust, is heated by underlying magma, and rises back to the seafloor carrying dissolved minerals. When this hot fluid meets cold seawater, the minerals precipitate out, forming chimney-like structures known as black smokers or white smokers, depending on their mineral composition. As mentioned earlier, these hydrothermal environments support unique ecosystems based on chemosynthesis rather than photosynthesis. The discovery of these communities in the late 1970s transformed our understanding of where and how life can exist. The bacteria that form the base of these food webs derive energy from the chemical compounds in the vent fluid, particularly hydrogen sulfide, which they oxidize in a process analogous to how plants use sunlight. This metabolic strategy allows them to thrive in perpetual darkness, using geochemical energy rather than solar energy to support life. The existence of these ecosystems has implications beyond Earth. As we search for potential habitats for life elsewhere in our solar system, scientists have become increasingly interested in worlds with evidence of both liquid water and internal heat sources that could drive hydrothermal circulation. Saturn's moon Enceladus, which ejects plumes of water ice from its south pole, and Jupiter's moon Europa, which appears to have a liquid ocean beneath its icy crust, are prime targets for this search. If life can thrive in Earth's hydrothermal systems without sunlight, perhaps similar environments on these moons could support life as well. This connection between volcanism and the search for extraterrestrial life illustrates how the study of Earth's processes informs our exploration of other worlds. By understanding how geological and biological systems interact here, we develop frameworks for investigating similar possibilities elsewhere. Earth becomes not just our home but our reference point, the baseline against which we measure the potential habitability of other planetary bodies. Closer to home, volcanic landforms offer windows into the past, preserving evidence of ancient events and conditions. Layers of ash and lava accumulate over time, creating a stratigraphic record that can be read like pages in a book. Radiometric dating techniques allow scientists to determine when different layers were deposited, while chemical and mineral analyses provide information about the composition of past eruptions. Fossils preserved in volcanic ash can reveal which plants and animals were present when the ash fell, offering glimpses of ecosystems long vanished. This approach has allowed researchers to reconstruct the eruptive histories of many volcanic systems, identifying patterns and cycles that may help predict future behavior. Some volcanoes show clear periodicity, erupting at relatively regular intervals, determined by how quickly magma accumulates in their reservoirs. Others display more chaotic patterns influenced by complex interaction between multiple factors. Understanding these historical patterns forms an important part of volcanic hazard assessment, helping communities prepare for and respond to potential eruptions. The challenge of living with volcanic risk varies greatly around the world. Some communities have developed sophisticated monitoring networks and evacuation plans, while others lack basic infrastructure for either detecting warning signs or moving people to safety. Cultural factors also influence how people perceive and respond to volcanic hazards. In some societies, traditional knowledge provides guidance for interpreting volcanic activity, while in others, scientific information may conflict with the religious or cultural beliefs about the meaning of eruptions. Navigating these differences requires sensitivity and respect from scientists and emergency managers. Effective risk communication must acknowledge diverse perspectives while providing actionable information that can help people make informed decisions. This approach recognizes that scientific understanding, while powerful, represents just one way of knowing and relating to volcanic landscapes, a complement to, rather than a replacement for, the cultural, historical, and spiritual dimensions of these relationships. As you continue to rest, imagine a volcanic landscape not during an eruption, but in one of the quiet intervals between events. Fumaroles, vents that release steam and volcanic gases, may mark the locations of subsurface heat sources. Hot springs bubble quietly, their waters rich in dissolved minerals. In some locations, gas seeps from the ground, sometimes visible as bubbles rising through mud or water, other times detectable only by its smell or by instruments designed to measure its composition. These subtle signs of ongoing activity remind us that volcanoes remain alive even when dormant. Below the surface, magma may be slowly cooling and crystallizing, or new magma may be ascending from deeper levels, gradually refilling reservoirs depleted during previous eruptions. Groundwater circulates through fractures in the rock, heated by contact with cooling magma bodies. Gases continue to escape from magma, working their way toward the surface through cracks and fissures. The volcano breathes quietly, exchanging heat and material with its surroundings in a constant, subtle dialogue. During these quiet periods, life reclaims volcanic landscapes. Pioneer plants take a root in cooling lava and ash, their roots helping to break down the rock and begin the process of soil formation. Insects, birds, and eventually larger animals return or colonize for the first time. The seemingly barren aftermath of an eruption gradually transforms into a living ecosystem, often one with unique characteristics shaped by the volcanic substrate and ongoing volcanic influences. In some volcanic regions, these processes have created habitats found nowhere else on Earth. The high-altitude paramo ecosystems of the northern Andes, dominated by distinctive rosette plants called frailejones, develop on volcanic soils in tropical mountains. The geothermal areas of Yellowstone host microbial communities adapted to extreme temperatures and chemical conditions. The island of Socotra, formed by volcanic activity in the Arabian Sea, harbors plants so unusual they seem almost alien. The dragon blood tree with its umbrella-shaped crown, the bottle tree with its bulbous trunk, the desert rose with its swollen base adapted for water storage. These and countless other examples illustrate how volcanic processes contribute to Earth's biodiversity by creating varied habitats and driving adaptive radiation, the evolution of new species to fill niches created by geological change. Island chains formed by hotspot volcanism like Hawaii and the Galapagos represent natural laboratories for this process, each island offering slightly different conditions and degrees of isolation that shape the evolution of their inhabitants. The concept of islands extends beyond physical land masses surrounded by water. Isolated volcanic mountains rising from plains, thermal springs in cold regions, or fumarole fields with unique chemical compositions can all function as ecological islands, hosting specialized communities adapted to their particular conditions. These habitat islands contribute to global biodiversity by providing refuges for species that might not survive in surrounding areas, as well as opportunities for new adaptations to emerge. As the night hours pass, consider how volcanoes have shaped the very ground beneath human settlements. Many of the world's major cities are built on or near volcanic deposits. Mexico City sits in a basin surrounded by volcanoes, including Popocatépetl, which remains active today. Naples, Italy, lies in the shadow of Vesuvius. Tokyo and much of Japan's population occupy regions shaped by the country's numerous volcanoes. Even cities far from currently active volcanoes may be built on ancient volcanic rocks or deposits. Edinburgh, Scotland, with its castle perched on an extinct volcanic plug. Clermont-Ferrand, France, surrounded by the cinder cones of the Chaîne de Chamdalwa. Puis, Auckland, New Zealand, built among a field of dormant volcanic cones. These locations were not chosen accidentally. Volcanic regions often offer advantages for human settlement: fertile soils, natural building materials, defensible positions on elevated terrain, and sources of water from springs fed by rainfall percolating through porous volcanic rocks. Throughout history, people have weighed these benefits against the risks of occasional eruptions, usually choosing to remain in volcanic regions despite their hazards. This risk calculation continues today, though with additional factors in the equation. Modern monitoring technology can provide warnings before many types of eruptions, allowing for evacuation and other protective measures. Building codes can require structures designed to withstand ashfall or other volcanic hazards. Land use planning can restrict development in the most vulnerable areas. These approaches don't eliminate risk, but they can reduce it to levels that communities find acceptable given the benefits of living in the volcanic landscapes. The concept of acceptable risk varies widely across cultures and contexts. Some communities maintain settlements in extremely hazardous locations due to economic necessity, cultural ties to place, or limited alternatives. Others may have lower risk tolerance and choose to relocate even after relatively minor events. These decisions involve not just scientific assessments of the physical danger, but also social, economic, and psychological factors, the complex calculus of human values and priorities that guides our interaction with the natural world. As dawn approaches, let your thoughts turn to the future of volcanic landscapes and our relationship with them. Climate change introduces new uncertainties into volcanic systems. As ice sheets and glaciers melt, the reduced weight on Earth's crust may affect magma generation and movement in some regions. Changes in precipitation patterns could alter how water interacts with magmatic systems, potentially affecting eruption styles or triggering landslides on volcanic slopes. Rising sea levels might impact coastal volcanic areas, changing how lava interacts with seawater or increasing the potential for tsunamis generated by volcanic activity. At the same time, volcanoes will continue to influence climate through their emissions of greenhouse gases, aerosols, and other compounds. The balance between volcanic warming and cooling effects has helped stabilize Earth's climate in the past, but this balance operates over geological timescales. On the shorter timescales relevant to human experience, individual large eruptions can still cause temporary climate disruptions, with potential impacts on agriculture, water resources, and other systems important to human societies. Understanding these interconnections requires collaboration across scientific disciplines and integration of different knowledge systems. Traditional ecological knowledge held by indigenous communities living in volcanic regions often includes observations gathered over many generations, providing insights into patterns and relationships that might not be captured in the relatively brief span of modern scientific monitoring. When combined with contemporary research methods, these multiple perspectives can create a more complete understanding of volcanic systems and their interactions with other Earth processes. This integrative approach extends to how we communicate about volcanoes as well. Artistic representations, from ancient paintings and carvings to modern films and literature, shape public perceptions and understanding of volcanic processes. Scientific visualization techniques translate complex data into images and animations that make volcanic behavior more accessible to non-specialists. Educational programs bring students into direct contact with volcanic landscapes, fostering personal connections that can lead to deeper engagement with both the science and the wonder of these dynamic systems. In recent years, virtual reality and augmented reality technologies have created new possibilities for experiencing volcanoes safely. Virtual field trips allow people to explore active craters or witness simulated eruptions without a physical risk. Three-dimensional models generated from satellite data or drone photography provide detailed views of volcanic features from angles that would be impossible or dangerous to observe directly. These tools extend access to volcanic landscapes beyond those able to visit in person, democratizing the experience and potentially building broader public support for research and conservation efforts. Conservation might seem an odd concept to apply to volcanoes, forces of nature that hardly need human protection, but many volcanic landscapes face threats from human activities. Mining operations extract pumice, scoria, and other volcanic materials for construction or industrial uses. Tourism development can damage sensitive areas through overuse or inappropriate infrastructure. Urbanization encroaches on volcanic slopes, both increasing human exposure to hazards and fragmenting natural habitats. Water extraction from volcanic aquifers can deplete springs and streams that support unique ecosystems. Balancing human uses with protection of volcanic environments requires careful planning and management. Many volcanic areas have been designated as national parks, World Heritage Sites, or other protected areas, recognizing their geological, ecological, and cultural significance. These designations provide frameworks for managing visitor access, regulating resource extraction, and preserving the integrity of volcanic features for future generations. They also create opportunities for education and research, helping build public understanding of and appreciation for volcanic processes and landscapes. This appreciation extends beyond the scientific and practical to encompass aesthetic and spiritual dimensions as well. The stark beauty of fresh lava fields, the perfect symmetry of a stratovolcano, the vivid colors of mineral deposits around the hot springs, these aspects of volcanic landscapes speak to something deep in human experience, a recognition of both power and pattern in the natural world. Artists, poets, and musicians have drawn inspiration from volcanoes throughout history, creating works that express this complex response of awe, fear, and wonder. For scientists, too, the aesthetic dimension remains important alongside the analytical. Many volcanologists speak of being drawn to their field not just by intellectual curiosity, but by the raw beauty and drama of volcanic processes. This emotional connection doesn't diminish the rigor of their research, but enriches it, providing motivation to understand these magnificent systems more deeply. In this way, scientific and artistic responses to volcanoes are not opposed but complementary, different expressions of the same fundamental human engagement with the world around us. As your night journey through volcanic landscapes draws to a close, return once more to the concept of breath, the slow exhalation of Earth's interior that volcanoes represent. Like breathing, volcanic activity follows rhythms both regular and variable. Like breathing, it involves exchange between interior and exterior, a constant conversation across boundaries. Like breathing, it is essential to the living system it serves, maintaining balances and cycles that have sustained Earth's habitability for billions of years. In this metaphor lies an invitation to relationship, not to see volcanoes as alien or separate from ourselves, but as expressions of the same planetary processes that have made our own existence possible. The calcium in our bones, the iron in our blood, the carbon in our cells, all these elements have cycled through Earth's systems, some passing through volcanic pathways on their journey. The air we breathe has been shaped by volcanic emissions over geological time. The land we inhabit has been built in many places by volcanic processes. We are not observers of Earth's volcanic nature but participants in it, our bodies and lives interwoven with these ancient flows of matter and energy. This perspective offers neither false comfort nor exaggerated fear. Volcanoes remain powerful and potentially dangerous, deserving of respect and caution. Yet they are also part of Earth's fundamental nature, not aberrations, but expressions of how our planet works and has always worked. In their cycles of activity and rest, destruction and creation, they embody processes essential to the world as we know it, processes that long preceded human existence and will continue long after we are gone. As you drift toward sleep, carry with you this image of Earth breathing through its volcanoes, not with the quick rhythm of human lungs, but with the slow patience of geological time. In this breathing lies both power and pattern, both unpredictability and order. It reminds us that we live on a dynamic planet, one whose seeming solidity masks constant movement and change occurring at depths and timescales beyond our direct perception. Yet through science, art, traditional knowledge and personal experience, we can begin to perceive these deeper rhythms, to develop a relationship with Earth that acknowledges both its hazards and its gifts. In this relationship lies a kind of wisdom, an understanding that sees volcanoes not merely as objects of study or sources of risk, but as teachers of patience, humility, and wonder in the face of forces that transcend human scales of time and power. The same volcanoes that occasionally disrupt human settlements also create conditions that have supported human flourishing over longer spans of time. The soils that nourish crops, the minerals that strengthen bones, the gases that help regulate climate, the land itself rising from the sea, all these volcanic contributions to human well-being balance against the periodic hazards these same systems present. Neither benefit nor risk tells the complete story. The full narrative encompasses both, woven together in the complex relationship between humanity and the dynamic Earth we inhabit. As night gives way to dawn, this relationship continues its evolution. New technologies expand our ability to monitor and understand volcanic processes. New approaches to risk reduction help communities live more safely in volcanic regions. New scientific insights deepen our appreciation for how volcanoes connect to other Earth systems. Yet alongside these advances, the fundamental nature of volcanoes remains consistent. They are windows into Earth's interior, expressions of its heat and movement, bridges between timescales and processes that might otherwise seem disconnected. In this consistency lies a kind of reassurance. For all the changes in human understanding and technology, the volcanoes themselves follow patterns established over billions of years. They remind us that we are part of something much larger and older than ourselves, a planetary system that has sustained life through countless transformations, finding balance not in stasis but in dynamic exchange and adaptation. This perspective invites a certain humility, a recognition that human control over natural processes has limits. We cannot prevent volcanoes from erupting, but we can learn to better anticipate their behavior. We cannot eliminate all risk from living in the volcanic regions, but we can make more informed choices about where and how we build our communities. We cannot separate ourselves from Earth's systems, but we can develop more sustainable relationships with them, ones that recognize both their constraints and their generosity. In these relationships lies the heart of our ongoing dialogue with volcanoes, not a conquest or a surrender, but a dance of mutual influence within the larger patterns of Earth's becoming. The same respect and attentiveness that allows scientists to better understand volcanic processes can guide communities in living more harmoniously within volcanic landscapes, appreciating their beauty and bounty while acknowledging their potential. Hazards. As your thoughts drift toward sleep, imagine once more the breadth of mountains, not as a single event, but as a continuing conversation, a back and forth exchange that has shaped both Earth and humanity throughout our shared history. In this conversation, both speakers have changed over time, yet the dialogue continues, evolving but never ending, part of the ongoing story of life on our dynamic planet. May this perspective bring a certain peace as you rest, not the false peace of imagined safety, but the deeper tranquility that comes from seeing oneself as part of natural processes rather than opposed to them. The same forces that sometimes threaten also sustain, their apparent contradictions resolved when viewed through the lens of time and interconnection. Within this understanding, even the most dramatic volcanic displays can be seen not as chaos, but as expressions of order, a different kind of order than human systems follow, but order nonetheless governed by principles and patterns that remain consistent even as their specific manifestations vary. Tomorrow, when you wake, perhaps you'll see the ordinary landscape around you with new eyes, noticing the volcanic origins of stones in a garden wall, recognizing the volcanic minerals in common clays and soils, or simply appreciating how the ground beneath your feet connects to Earth's deepest layers through pathways of heat and movement that have shaped our world since its beginning. For now, as sleep approaches, let the image of Earth breathing through its volcanoes accompany you into dreams, a reminder of the living, dynamic nature of the planet we call home, and of our own place within its ancient rhythms of destruction and creation, movement and rest, exchange and transformation. In this image lies not fear but wonder, not anxiety but acceptance, not a separation, but connection to the profound processes that have made our world what it is, processes that continue even as you sleep, maintaining the delicate balances that allow life to flourish amid the vast energies of a living planet. And as the first light of dawn touches your window, remember that somewhere in the world, a volcano is awakening or falling silent, extending or cooling its flows, building or reshaping its form, breathing in its slow monumental way, participating in Earth's ongoing becoming. In this becoming, we too have our place, as observers and narrators, as recipients of both hazard and benefit, and as stewards of knowledge passed from generation to generation, helping us live wisely within the embrace of mountains that breathe fire,